What's up guys, it's Simon Fiaz and today's video is on AQA A-Level Chemistry Paper 2, 2023 Paper 2. It's just the reason why using conical flask instead of a beaker would give more accurate results in this experiment. Reduces loss of liquid droplets. Use figure 2 to calculate the reaction at 2 minutes. So what you do is you go to 2 minutes, so 2 minutes here, you draw a tangent, then find the gradient of the tangent, and the units is just going to be this, so grams per minute to power minus 1, and the rate, yeah, it just depends on your answer, your gradient. So if I did the gradient right now, at 2 minutes, so yeah, 0.50 over 0.05. No, sorry, the gradient 0.50 plus or minus 0.50 is a gradient. Suggest why sketching figure 2 curve expect when this much of the hydroxide excess of sodium NaHCO3. Well, what's going to happen is the curve is going to be steeper at first and then flattens at the same point in y-axis, so like something like that. Suggest why chloroethanoic acid is stronger acid than ethanoic acid. Chlorine is an electron is electron withdrawing group / negative inductive effect, increasing the polarity of OH bond. Cl's electron withdrawing group / negative inductive effect, increasing polarity of OH bond. Complete table 1 by calculating the missing values. So that's increasing by times by 5/4. That stays the same, and that stays the same. Because 0.50 divided by 0.4 is 5/4. Therefore, 1.00 times by my answer. But okay. Is is A in the rate equation? No, it's only B and H. Therefore, I don't care about A. It doesn't affect the rate because it's not in the rate equation. So that stays the same. Then if I look at the rest, well, that clearly decreased. 0.64 divided by 1.00. That's 16 over 25 times in by 16 over 25. H, concentration H plus stays the same. A, I don't care, it's not even in the rate equation, so it's only B. Well, with B, it's squared, so it's going to be the square root of 16 over 25, which is, no, sorry, it's going to be 16 over 25. Yeah, the square root of that. 4 over 5, and then 0.20 times by my answer, 0.16. And then again, the final one from 0.30 divided by 0.16, 15 over 8 times by 15 over 8 here, 0.6 divided by 0.10 times by 3 over 5, and 15 over 8 times by 3 over 5, 9 over 8, 1.64 times my answer. But remember, B is squared, so it's going to be 15 over 8. 15 over 8 squared times by 3 over 5, and then do 0.64 times my answer, 1.35. That is really tricky though. The concentration A, that's really sneaky. Sorry, including it, but it's not in the rate equation, so it's not going to affect it at all. So then 1 to 2, that's going to be 1, so it's the same because so does B and H. And then the third one, well, H stays the same because it's H plus signs, and therefore, and also the rate times by 16 over 25. Therefore, concentration of B, well, it's got to be the square root of 16 over 25. And therefore, I'm going to do 0.20 times by that, which is 0.16. And then for 3 to 4, 0.10 to 0.06 times by 3 over 5. And then 0.16 to 0.30 times by 15 over 8. But remember, B is squared, so 15 over 8 squared times by 3 over 5, and then do 0.64 times by that to give you 1.35. Introduce the rate determining step, the slowest step in the reaction. It's definitely going to be step. Well, look here, two B's and 1H plus. There we go, 2 B's, 1H plus has been used. So step 2, as by the end of step 2, 1H plus and 2 B's have been used, and that is directly in the rate equation as well, and it has to be this like that. Question 3, figure 3 shows an intermediate form of the first type of nucleophilic addition elimination mechanism. Complete figure 3. So I've got, this one's really unique kind of mechanism question if you ask me, but basically I've got my CH3, CH2, C double bundle, Cl, oxygen, methanol, hydrogen here, 2 lone pairs of electrons, carbon's partially positive, oxygen partially negative, that's partially negative, goes here, doop, doop, then that's got a lone pair of electrons, and say, yeah, relevant lone pair of electrons. Once formed a double bond, CCl bond must break, and that goes there as well. So they can really try to, different ways of asking you about mechanisms and all that. But the truth reality is, if you've, gone through these mechanisms a lot of times and you memorize all the steps and you know what exactly you're doing, you're gonna know exactly what to do any type of question they ask you. Because it's the same, show the curly arrows, etc., etc. And that's it. Then it says another type of question like this. Complete figure 4 to show the reaction species in curly arrows. Give the name of the reaction mechanism. I already know the name, so I'm going to do that first. Get that nice mark. Electrophilic substitution. The curly arrows was definitely one here. And remember, this is NO2. So what it's going to be like? It's going to be like this. I'm still going to have this methyl group here. That stays the same. But I've got this NO2 plus with nitrogen positive charge, and it goes there. But actually, that's not correct as well. The reason that's not correct is because look at the horseshoe ring; it's pointing downwards. So my NO2 therefore. So you have to be extremely specific. So we've got the benzene ring, CH3 methyl group there. Then the NO2 plus is something like here, somewhere here. And then here to here, and then that explains why the horseshoe ring's there. And then yeah, there, electrophilic substitution, 4 marks. Then it says figure 5 shows the reaction species evolved in the first step of the mechanism. Complete figure 5 shows the structure of the intermediate form of curly arrows involved in its formation. Name of the mechanism, nucleophilic addition. Nucleophilic nucleophilic addition. Nucleophilic addition. What happens? Lone pair of electrons, H minus goes there. Goes there. That's the first thing. Then you've got this oxygen with lone pair of electrons negatively charged, H plus sign, and it bonds to the H, and then you form OH here. But you don't need to, it just says show the structure of the intermediate. So yeah, that should be fine. So then instead of this, so that get rid of the lone pair electrons and that, so it just should be oxygen negatively charged because that's the only step it wants. Use IUPAC names. I use IUPAC rules to name isomer W. So I've got methane, ethane, propane. I've got 3 bromo, A, B. You need to do alphabetical order. So 3 bromo first, propane. And I've also got nitrile group, propane, nitrile. 3-bromo, propane, nitrile. Draw reaction 1, produce a mixture of W and 2 of the isomers. Draw the structures of 2 isomers. Explain by considering mechanism of reaction why all 3 isomers are formed. It's a 6 marker. So stage 1 isomers found CH3 CHBrCN exists as 2 optical isomers / enantiomers. Stage 2 mechanism. So with the mechanism, I've got this. I'm just going to draw it here. I don't want to. Well, actually, no. I'll just do it there. Then instead, C to 1C, CN, H. It doesn't even ask me to name this mechanism, but it is electrophilic addition. Hydrogen bromide, hydrogen partially positive, Br is partially negative, and it goes there, and then it goes there, right? Then what happens is I've got my stuff added. So I've got my hydrogen here, I've got my hydrogen here, I've got my CN here, I've got my hydrogen here, I've got my CN here. CH3 CHBrCN, and then what happens is either the hydrogen can be here, and then this carbon cation organic containing positive charged carbon, and then it goes here, or it's the other way around, and I've got this here, and then that's positive charge, lone pair of electrons, and the Br minus goes there. And that's obviously going to be, this is primary carbon cation. I'm just going to represent it as one O carbon cation. This one, well, it's attached to 1, and this that's another carbon, so that's secondary carbocation. And then stage 3 optical isomerism. Stage 3 optical isomerism. Well, the 2-bromo isomer has a chiral carbon with 4 different groups attached to it. yeah, 1, 2, 3, 4, 1. Yeah, because if you look here, this 2 bromo ice 2 carbon 2 bromo isomer, that's one, that's a methyl group, that's a nitrile group, and that's a Br group. And once it's bonded, but in this case, the primary carbocation, that's a hydrogen, both the same, so it's not going to have carbon. It's not going to have a chirocarbon. Had chirocarbon, 4 different groups attached to it, and then drawing it out, I've got C. Actually, no, I don't even need to say that. Draw it out. So it's optical because secondary, I'm saying which one is a secondary carbocation is planar, so can be attacked from above slash below, and then show that being attacked from above or below. So I said attack from above slash below, positive charge, lone pair electrons Br minus CH, yeah, I can attack here, or lone pair electron Br minus attack here. No, there. CH3, CHBr, CN exists as 2 optical isomers slash enantiomer stage to the mechanism. Stage 3 optical isomerism. The 2 bromo isomer has a chirocarbon 4 different groups attached to it. Optical is a secondary C plus is planar, therefore can be attacked from above slash below, and then show that. Identify the reagent that is warmed with isomer W in reaction 2. So I'm going from that is warmed with isomer W in reaction 2 here to here. What's happened? I have replaced this Br group with an N group. So KCN, aqueous and ethanol. Aqueous and ethanol. Say the region and reaction conditions needed for reaction 3. So I'm going from this nitrile to an amine. So hydrogen and nickel, and then let's draw it out. So NCCH2, CH2CN plus how many hydrogens am I adding? Plus 4H2 to form H2N bracket. I should draw it like write it down like this: H2N bracket CH2 4 NH2 H2 and nickel, KCN, aqueous and ethanol, and there you go. That's what this is also called catalytic hydrogenation, hydrogen and nickel catalyst slash PT or PD, and then plus 4H2 to form this. Deduce the values of x and y in this equation. X is equal to 5, y is equal to 9. Just balancing it out really. 5 here, and y is going to be 9 H2Os. Draw on figure 2 another section of nylon 4,6 polymer showing 2 hydrogen bonds between the 2 sections. We've got here a carbon double bond O, H2C4, C double bond O again, and H, CH2. All I'm doing is drawing this out again. Another section that I'm showing 2 hydrogen bonds, and H there. Obviously, I should directly do it, but I guess this is fine. And then that's 1 hydrogen bond, and then lone pair of electrons here. That's another hydrogen bond, but it should be like directly aligned, so it's just a straight like bond like that. Identify the bond that causes the absorption at 1725 centimeters to power minus 1. So I'd go to my periodic table, datasheet table A, 1725, it's the carbonyl bond. C double bond O. 13C NMR spectrum of Z. I haven't gone through that in class, can't do that. Can't do that. Can't do that. I can't do that. Can't do that. Can't do that. So the only part I could do is 5.1. Just reading 1725 S minus 1 is C double bond O carbonyl functional group. A student plans a series of chemical tests to confirm the identity for organic liquids. Add potassium dichromate, 6 solution, warm gently. Add failing solution, cool ice water. Add sodium hydrogen carbonate solution, test any gas produced with light splint. Add bromine water and shake at room temperature. Identify the missing reagent needed in step 1. H2SO4, sulfuric acid. Use H2SO4. In addition to the missing reagent test 1, there's a mistake in the method for 2 of the other 2 tests. State the 2 mistakes, suggest how each of the mistakes should be corrected. And cool in ice water? No. Cool test 2. When do we ever cool it? We warm in a water bath. Mistake 2, so that's mistake 1. Mistake 2, add hydrocarbonate solution, test any gas produced with a lighted splint. No, no. That's such an obvious mistake. But I guess students, including myself, will fall for it because I fell for it as well. That's not. No, you need to. So the mistake was that test any gas produced with lighted splint. Test gas produced with lighted splint. Bubble the gas into lime water. Bubble gas through lime water. Sodium hydrocarbonate solution. Yeah, bubble the gas through lime water. Identify the main missing regions added and mistakes are corrected. Identify the liquids J, K, and L and M that would react in each test. Say the expected observation for each reaction. 8 marks. And it's literally how well you know your practical skills. How well you know the test for functional groups and all of that. So liquids that react in test 1. Test 1, add potassium dichromate 6 solution and warm gently. Well, first thing I'm going to do is I'm just going to write down all the expected observations. Because they're going to be, write down the expected observations. That's what I'm going to do first. Liquids that react in test 2, add failing solution cooled in ice water, blue to brick red precipitate, blue solution gives a brick red precipitate. Liquids that react in test 3, the observation, lime water turns cloudy, lime water turns cloudy, and test 4, the expected observation, there's no, that's not it, it's bromine water and shake at room temperature, orange solution decolorizes. Oh yeah, or orange to colors, but decolorize is fine. So the liquids are reacting test 1. Well, test 1 is orange solution to green, and it is Add potassium dichromate 6 solution, warm gently. Now, potassium dichromate 6 solution won't work for ketones, so that's out of the equation. That's out of the equation. Actually, no, sorry, no, sorry. 6.2, 6.3. I need to firstly colorless gas turns the lime water cloudy. I can't just say lime water turns cloudy. An orange solution decolorizes, goes colorless. So then test one, potassium dichromate 6 solution warm gently. Well, it's not going to be, sorry, yeah, it is going to be J and M. It's not going to be, because J and M, right, J and M, you put carbon here, that's what, let's say, they both got J has an OH group, right, and that is a primary alcohol. M definitely can as well. So J and M, J and M, J and M is not going to be, definitely not going to be K and L, because I look at K, that's a, sorry, that's a primary, secondary, tertiary alcohol, so we can't oxidize that. And this one, again, that's just, yeah, we can't do that as well. Then for test 2, failing solution. Well, failing solution only works for aldehydes in this case. So it's just gonna be M. Yeah, because it's definitely, it can't be J or L because they both got the OH groups. No, in just aldehydes. Left with K and M. Look at K. That's a ketone. Therefore, the answer must be M. I think I just confused ketones with aldehydes. Ketones have the functional group at the middle, in the middle. Aldehydes have at the end, because that's why for the first part, when I was saying test one can't be J and M, because I thought they were both ketones, but in reality they're both aldehydes, because they both got a functional group at the end of the carbon chain. No, sorry, J is carboxylic acid. Yeah, but they both got the carbonyl group, functional group at the end of the carbon chain. That was an aldehyde, whereas the ketone's in the middle. So I just got confused between that. So M, yeah, the aldehyde only, and therefore it must be M. It can't be J, it can't be L, and it definitely can't be K. That's a ketone. Same with L. And J's got an OH group, so therefore we can't use that as well. Test 3, add sodium hydrogen carbonate solution, test any gas produced with lighted splint. J and L, because they're both carboxylic acids. Look, COOH, that's not got an OH, that's not got an AH. That's J and L. J and L. Use sodium hydrocarbonate to test for carboxylic acids or hydrogen carbonate. Add bromine water and shake at room temperature. Well, what does bromine water test for? What does bromine water test for, right? So we've got J and L. Colorless gas turns lime water cloudy. Liquids are react and test for, but add bromine water to shake it to room temperature. What does bromine water test for? It tests for the presence of double bonds. And if I look at here, which one is it going to be, right? Well, it's definitely not going to be J or L since both of those are carboxylic acids, right? And then left with K and M. Well, the thing about K is obviously it's a ketone, and yeah, whereas with M, yeah, it can test for M. No, sorry, not. It can't be J or L, so I'm left with K and M. Oh my days! 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 How did I not spot that? What does bromine water test for? I'm gonna say it again. Bromine water tests for the presence of double bonds, right? J doesn't have a double bond, that's just C double bond O. L C double bond O. M C double bond O. K, that's a C double bond O. But what about this? That's a double bond, therefore it is going to be K, the only liquid that can react and test for. And that's tricky, man. Explain why fractional distillation preferred simple distillation and suggest labels that should be added to positions S, T, and U. Whereas T is going to be water out, U is water in, S is what? Fractionating column, fractionating. Why is fractional distillation preferred to simple distillation? That's what it says, right? Because liquids K and M are likely to have similar boiling points. So that's water out, that's water in. And that's your fractionating column. Question 7. Calculate the volume in centimeters cube of propanone in the gas syringe. A gas syringe that does not have any graduations is calibrated using known mass of propanone, boiling point of that. Seal gas syringe containing this much propanone at a temperature of this, pressure of this, calculate volume in the gas syringe. Alhamdulillah. So I'm going to use PV equals nRT. Therefore, V equals nRT divided by P. Very simple. Then I'm going to convert the units. Well, first things first, I need to find out the moles of propanone. The moles of propanone is 0.146, the mass over the MR. MR times by 8.31 times by the temperature in Kelvin, 95 degrees Celsius. I want in Kelvin at 273. 95 plus 273, 368, all over the pressure in pascals, 103,000 pascals. Now remember, volume in the ideal gas equation gives it me in meters cubed. I want it in centimeters cubed. I want it in centimeters cubed. So dm cubed is in the middle, like D block is in the middle of the periodic table. Cm cubed is here. Meters cubed is here. Or is it the other way around? No, it's perfectly fine like this. You have to go from meters cubed to centimeters cubed. I need it times by 1,000. Times by 1,000 again. So I need times by a million. So first things first, let's work out the volume. 0.146 divided by 58.0 times by 8.31 times by 368. I'll just say 95 plus 273 in case I wrote it wrong. I have 103,000 and then times by 10 to the power 6 times by a million, and I should get 75 centimeters cubed. Calculate a decrease in volume. Gas syringe is then cooled to 75 degrees Celsius without changing the pressure. the decrease in volume. In order to do that, all I have to do is first thing find the decrease in temperature. Well, 95 plus 273 is obviously 368. And this plus 273, 75 plus 273 is 348. So it's going to be 348 divided by 368 times by 75. Because that's my answer. So 348 divided by 368 times by 75. I get 71. And then to find out the decrease in volume, I've gone from 75 centimeters cubed to 71. So the decrease is 4 centimeters cubed. So cool to 75 degrees Celsius, calculate that in Kelvin, 348. The original temperature in Kelvin is that. Use that factor, times it by 75 volume, then you can find out the new volume. Then do 75 minus that new volume to get 4. Calculate the uncertainty that is causing the volume of centimeters cubed of propanol. Total uncertainty to measure the mass is 0.001 grams. Calculate uncertainty that causes the volume of centimeters cubed of propanol. Question 7.1. In the mass. So the mass of propanol is 0.146. So I can use this to find out the percentage uncertainty as 0.685%. Then use this idea to calculate the volume uncertainty. Times by 75. That's going to be, my answer is 0.685 divided by 100, because that's a percentage, but I just want the uncertainty, times by 75. 0.51. 0.5. Let's say 0.5 centimeters cubed. Question 7.4. A 600 centimeters cube sample of propanol is mixed with 2800 centimeters cube of oxygen contained at this. Mixture is ignited, reaction is complete, remaining mixture maxes of gases. Remaining mixture of gases cooled to 60 degrees Celsius, 100 kilopascal. Calculate the total volume of the gases of the remaining gas mixture. So 600 centimeters cube of propanol is mixed with 2800 centimeters cube of oxygen. First thing I notice is it is a 1 to 4 molar ratio. So 600 times by 4 is 2400, right? That tells me 400 centimeters cubed of oxygen is in excess, right? So I've got 400 here. So I'm already going to have 400 centimeters cubed here remaining. And therefore to find out this, well, it's just going to be 600 times by 3, 1200. Total volume 1200 plus 400, which is 1800. Oh, sorry, that's a 3. That's what it said 2. So that's 400, and then that's going to be 1800 because 1 to 3 mole ratio. So 1800 plus, 600 times by 3 is 1800, not 1200, plus 400 to give me 2200 remaining. Now the tricky part here is most students, including myself, would think about this. But look at that state symbol. That's a liquid. That's not a gas. So I don't care about the volume of that. It's not a gas, it's a liquid. So yeah, that's in excess, 400 centimeters cube oxygen remaining, and then use a molar ratio to find out the volume of this. 1800, 600 times by 3, 1800 plus 400, 2200 centimeters cubed. Complete the equations. Equation for the hydrolysis of triester and palm oil under acidic conditions. 3CH, 3CH214 COOH plus CH2OH CHOH, CH2OH. 3CH3 CH2 14 COH plus CH2OH plus CH2OH CHOH CH2OH. All I've done is that goes. You've got a hydrogen here, CH3 CH2 14 COH. You've got three of them, 1 2 3, so you need a 3 here. And then for here, all I've done is added an OH here for each of these. So CH2OH, CHOH, CH2OH. That's it. That's it. Calculate value for enthalpy of combustion of palmitic acid in the experiment. So delta H. Well, delta H is Q divided by number of moles. Q equals MC delta T. Moles equals mass over mR. So first thing I'm going to use Q equals MC delta T, where M is the mass of water and that's in kilograms, so I need 100. It's going to be 150 grams times by 4.18 times by temperature change 37.5 minus 23.9. I'm going to leave that there. Then the moles is mass over mR, mass of the acid. So 387 milligrams, but I want it in grams. Milligrams to grams. Well, I want to go from grams to milligrams. I times by 1,000. I have to go from milligrams to grams. I divide by 1,000. It's going to be moles equals 0.387 divided by the mR of palmitic acid, and I'm just going to have to calculate that out, unfortunately. So palmitic acid is that 12 plus 3, 15 plus 12 plus 2, 14 times by 14 plus 12 plus 16 plus 16 plus 1, 256. Yeah, 256 divided by 256. And then delta H is your Q. But remember, this is in kilojoules multiplied minus 1. Q is measured in joules. So I need to divide my Q divided by 1,000. 150 times by 4.18 times by 37.5 minus 23.9 divided by 1,000. Keep the answer. Divided by 0.387 divided by 256. 5640. And the final trick a lot of students fall for, including myself, but since I've been, I fell for it many times, I've kind of learned now from my mistake, is that the temperature of the water increases. So that tells me that it's exothermic, as temperature increases, therefore exothermic. State how the data block values calculated in question A produce like differ, give one reason other than heat loss. Less exothermic due to incomplete combustion. Less exothermic due to incomplete combustion. Calculate empirical formula biofuel. I've got, firstly, find out the rest of sulfur. It gets 33.05 a year, 33.05. Then what I'm going to do is I'm going to do carbon to hydrogen to oxygen to sulfur, and I'm going to find out the moles for each one. 37.08 divided by 12 to 5.15 divided by 1 to 24.72 divided by mol of oxygen, 16 to 33.05 divided by the mol of sulfur, which is 32.1. And then you see the smallest mole ratio, and then you divide it by that. And I'm not going to go through that final part. And then you should get empirical formula, whole number ratio as C6H10O3S2. C6H10O3S2. Less exothermic due to incomplete combustion. Suggests one of the possible environmental problem with complete combustion is biofuel. Acid rain and SO2. Sulfur dioxide is the formula pollutant responsible for this problem. Question 8.6. Calculate an approximate value for the enthalpy delta H for the fermentation of glucose. Now this question I'm not sure how to do, so I'm going to leave this question. Use data to calculate. I'll do that in a separate video probably. Use data to calculate standard enthalpy change for this reaction. A little f tells me it's formation data, but it says already there already, so never mind. So enthalpy of products minus enthalpy of reactants. So C2H5OH minus 235. Oxygen's element by itself is 0. Enthalpy of products minus enthalpy of reactants 2 times by CO2, 2 times by minus 394 minus 788 plus 3 times by H12, 3 times by minus 242 minus 276 minus 235 minus 788 plus minus 726 1279, and obviously show that it's positive as well. Deduce the general formula for the ketene homologous series. CnH2n minus 2O, CnH2n minus 2O, CnH2n minus 2O. I don't know why I did the oxygen so big, it should be a bit smaller. Yeah, CnH2n minus 2O. Complete the mechanism by the 3 color of any relevant lone pairs of electrons. So first things first, step 1, I'm splitting it up to this decomposition of ethanoic anhydride. So how do I do that? Well, I've got H3C, C double bond O there. Well, I know the oxygen is negative, so it's got to be like that. And therefore that will make the carbon positive, and that will make the oxygen negative. And then to form that, well then it goes like that. Pretty simple. And what happens here? Well, the lone pair of electrons here acts as base, takes a proton, and then it goes to there. And you've got that and that. So let's go through it again. So, well, it can either be obviously this way or this way, right? And the reason it's got to be this way is because that would make the carbon positive because it's broken a bond, and therefore that would make the oxygen negative. Then left carbon has a spare electron, wants to reform double bond. Lone pair of electrons here acts as base and takes a proton. And once it takes a proton, then left carbon has a spare electron, wants to form a double bond. And then it says chemical reaction relation between the rate constant K and temperature T is shown by the Arrhenius equation. Calculate T1. T1, the rate constant K is that. Wait, so what does it want me to do? Oh, we just want me to calculate temperature. Okay, so first thing I'm going to do is I'm going to take the logarithmic form. So ln K equals ln A minus EA over RT. Add EA over RT, you get EA over RT equals ln A and minus ln K times by RT. EA equals RT ln A minus ln K. RT EA divided by ln A minus ln K. And therefore, to find T, it's just going to be EA over ln A minus ln K divided by 8.31. Okay, EA is that in kilojoules, but I want it in joules because EA is measured in joules, so it's going to be 34,500. I'm just going to put in my calculator, so I'm going to obviously walk through it. 34,500 divided by ln A, shift ln A, 1.0 times by 10 to the power 12, minus shift ln K, 2.48 times by 10 to the power 8, and then divide my answer by 8.31, and then I get 500 Kelvin. And I prefer to do it this way, because I'm so used to the logarithmic form now, because so many questions ask about logarithmic form. In this case, you don't need to. You can just say K over A is E to the power minus E over RT, and then do it like that. But I prefer to do it this way. Sketch the Maxwell-Boltzmann distribution curve of molecular energies at gaseous, and obviously we want to label it as well. So number of molecules on the left hand side, number of molecules, energy, that does not look like energy, arrow there. So normal one is just going to look something like this, and this is going to be the activation energy, EA, and that is going to be T1. At high temperature T2, what happens is that when it goes like this, then it goes like that and that, something like that. Eventually they'll be similar together, so that's T2. Number of molecules, energy, label activation energy here, that's T1, that's T2. Explain why the rate of reaction is faster at T2. At T2, more particles have energy greater than or equal to the required activation energy. They always, like, for some reason, if you're always unsure, I'll always say that at T2 for rate of reaction of that, more particles have energy greater than or equal to the required activation energy. Molecules energy, T1 just like that, T2 higher, but then it goes lower and then meets there. That's the activation energy. That's energy, that's number of molecules. At T2, more particles have energy greater than or equal to, more particles have energy greater than or equal to required activation energy, therefore faster rate of reaction at T2. And that is the end of past paper questions.